Welcome to the deep dive. Today we're tackling something pretty wild, a real paradox. Carbon. It's like super rare in the Earth's crust, right? Only 0.02%, and even less in the air, 0.03%.
Tiny amounts.
Yet, it's everywhere. The foundation of life itself, our food, clothes, medicine, everything.
It seems impossible, doesn't it?
So how does that work? How can something so scarce be so, well, fundamental? That's our mission today, to unpack the why behind carbon and its knack for forming millions of compounds.
And the answer, really, it boils down to carbon's atomic structure, how it behaves.
Its personality, almost.
You could say that. It's all about how it bonds with other atoms. We'll look at its unique way of sharing electrons, its versatility, something called catenation, and, link it all to things you use every day, fuels, soaps, that kind of thing.
Okay, let's dive into that atom then. Carbon's number 6. 2 electrons inside, 4 on the outside shell. Now, atoms like having 8 on the outside to be stable, right?
Exactly. They want that full outer shell like the noble gases.
So for carbon, with 4, does it gain 4, lose 4? That sounds tough.
It is tough.
Yeah.
Energetically speaking, gaining or losing 4 electrons just takes, well, a huge amount of energy. It's not really feasible.
Oh, okay.
So carbon does something quite elegant. What's fascinating here is it shares its 4 outer electrons with other atoms.
Covalent bonds.
Precisely. Strong covalent bonds. And by sharing, it effectively gets access to 8 electrons, achieving that stable configuration.
Right, and that's different from ionic compounds.
Very different. Ionic compounds swap electrons, forming ions. Covalent compounds share. And this sharing generally leads to lower melting and boiling points. Think about vinegar, acetic acid, it's liquid at room temp. Ethanol, too.
Okay.
That's because the forces between the molecules are weaker, even though the bonds within the molecule are strong. Also, they usually don't conduct electricity. No free ions floating around.
So this sharing gives it flexibility. It can share 1 pair of electrons for a single bond, like with hydrogen.
Methane, CH4 is the classic example there. 1 carbon, 4 hydrogens.
Or 2 pairs for a double bond, like in oxygen.
Or even 3
Right.
for a triple bond, like nitrogen, N2O2. Carbon does double and triple bonds too, which adds even more variety. But that ability to form 4 single bonds, its tetravalency, is really central.
Okay, tetravalency, 4 bonds. Got it.
Now, if we connect this to the bigger picture, carbon has these 2 amazing properties that work together.
Like superpowers.
Superpowers, I like it.
Well, first is catenation. That's its incredible ability to bond with itself, other carbon atoms.
Forming chains.
Exactly. Long chains, branched chains, even rings. And these carbon bonds are remarkably strong and stable, much more so than, say, silicon bonds. Silicon can form chains, but they're much less stable.
So carbon chains don't just fall apart.
Not easily, no. That stability is crucial for complex molecules, like in biology. And the second superpower, that tetravalency we mentioned.
Forming 4 bonds. Right. So it can link up with itself and form strong bonds with lots of other elements. Hydrogen, oxygen, nitrogen, sulfur, halogens, you name it. And because carbon is a relatively small atom, these bonds tend to be very strong and stable.
So it's the combination then, catenation to build the backbone and tetravalency to attach everything else.
You've got it. That's what creates the sheer mind-boggling diversity of carbon compounds. Millions of them.
Wow.
And you see this diversity perfectly even when it's just carbon. Think about the allotropes of carbon.
Like diamond and graphite.
Exactly. Same element, totally different properties. Diamond. Each carbon bonds to 4 others in this rigid 3D network. Makes it incredibly hard, right? The hardest natural substance. And it doesn't conduct electricity.
Okay.
Graphite. Each carbon bonds to only 3 others in flat hexagonal layers. That 4th electron, it's kind of free to move between the layers.
So that's why graphite conducts electricity.
That's it. And why it's soft and slippery, the layers slide past each other. Same atoms, just arranged differently. It's amazing, isn't it? There's also Buckminster fullerene, CCC, shaped like a soccer ball. Another arrangement, another set of properties.
It really shows how structure is everything. Okay, so we have this versatile backbone. What about when other things attach? You mentioned functional groups.
Right, functional groups. These are specific clusters of atoms, like an ACOH group, which makes an alcohol, or a COH group, making a carboxylic acid.
And they determine the chemistry.
Largely, yes.
Yeah.
They give the molecule its chemical personality, you could say, often regardless of how long the carbon chain is. And of course, a key reaction for many carbon compounds is combustion, burning them.
Fuels, basically. They burn, release energy, light, and carbon dioxide, CO2 too.
Correct.
Yeah.
And interestingly, how they burn tells you something. Saturated hydrocarbons, like alkanes, tend to burn with a clean blue flame, complete combustion.
Right.
Unsaturated ones, with double or triple bonds, often burn with a yellow sooty flame. That's incomplete combustion, leaving behind unburnt carbon.
Okay, that makes sense. What about other reactions? You mentioned everyday uses.
Oh, loads. Take addition reactions. Unsaturated compounds, like those in liquid vegetable oils, have double bonds in their long carbon chains.
Okay.
We can add hydrogen across those double bonds. That's called hydrogenation. Usually needs a catalyst like nickel or palladium and turn them into saturated fats.
Like turning liquid oil into solid vegetable ghee or margarine.
Exactly. That's a huge industrial process. Or think about ethanoic acid.
Vinegar.
Yep. A 3–4% solution is vinegar. Great preservative. But it also reacts with alcohols.
To make?
Esters. These often have really pleasant, fruity smells. They're used all the time in perfumes and as artificial flavorings.
Ah, okay. So that sweet smell in candy or perfume might be an ester. Cool. And what about cleaning? Soaps.
Right. Soaps and detergents. Brilliant chemistry. A soap molecule has two ends. One end, the head, is ionic and loves water hydrophilic.
Hydrowater, philic alkyl loving. Got it.
And the other end is a long hydrocarbon tail, which hates water but loves oil and grease, hydrophobic.
Havovic hating. Okay. So when you put soap in water with some greasy dirt, the hydrophobic tails bury themselves in the grease droplet. The hydrophilic heads stick out into the water.
Forming a little ball around the grease.
Exactly. These little clusters are called micelles. The grease is trapped inside, and the water-loving heads on the outside let the whole thing get washed away by the water.
That's clever.
Yeah.
But what about hard water? Soap doesn't work so well then, does it? You get that scum.
Ah, yes, the dreaded soap scum. That's the problem. Hard water has calcium and magnesium ions dissolved in it. Soap molecules react with these ions to form an insoluble precipitate. That's the scum. It's useless for cleaning and leaves a residue.
So what's the solution?
Detergents. They have a similar structure, a water-loving head and an oil-loving tail, but the head part is different chemically, often a sulfonate or an ammonium salt group.
And that makes the difference. It does. These detergent heads don't form insoluble precipitates with the calcium and magnesium ions in hard water, so they keep working, forming micelles and cleaning effectively, even when the water's hard.
So detergents basically solve the hard water problem for cleaning.
Pretty much, yeah. A great example of designing molecules for a specific job.
Okay, so stepping back, what does this all mean? Carbon. It's rare in the grand scheme of the Earth's crust yet. Its simple ability to share electrons, link with itself endlessly, and bond with so many other things, it just unlocks this incredible world of compounds.
It really does.
It's fundamental to life, energy, material, practically everything.
It is truly astonishing. And when you think about it, that deep connection between carbon chemistry and, well, us, our lives, our technology, is profound.
Yeah.
Understanding its fundamental versatility, well, it's key. It means we can keep exploring and maybe find new, perhaps more sustainable ways to use carbon chemistry to tackle future challenges. There's still so much potential there.